Welcome. In this movie, I want to answer a question I keep getting many times, and it's not easy to answer for a generic purpose case. I have a microstructure, I have a sample. Can I see a specific population of scatters using small angle scattering instrument? In other words, I have a piece of metal, piece of ceramic, piece of plastic, whatever else is my sample of today. And by some means, for example, SEM, TEM, or any other microscopy technique, I know I have some population of scatters. Let's call them XYZ scatters in this case. And I need to characterize them because, for example, I want to do an in situ measurement using small angle scattering. And so I want to know, can I see them and can I characterize them above everything else which is in the sample? So the question is, can I do it? Will I see it? And so this is actually quite complicated question because even though I can see the particles in TEM, take another pick, optical microscopy, SEM, whatever else you're using. Why cannot I see them? Why shouldn't I be able to see them in small angle scattering? Well, it gets more complicated because in most materials you will have multiple populations of scatters. In metals, you're going to have grain boundaries and possibly grains with different compositions. Grain boundaries are basically a garbage collector. Impurities aggregate on grain boundaries, and so they have different contrast, and obviously they will scatter. Grains may have different composition, therefore they're going to have a different contrast, they will scatter. So, and while in transmission microscopy or any other microscopy, we can select a magnification which then allows us to study material at a specific range of length scales. Also sometimes image contrast mechanism by doing some kind of variation of TEM. Small angle scattering, I'm going to call it SAS in this little presentation here, sees everything. It just sees everything at the same time. It cannot easily distinguish them. There are some ways to try to do that, but it's not easy to do. And all the scatter sizes scatter at all scattering vectors. So you cannot simply say, I am going to scatter at high Q, so I won't see the small size, large particles, the small Q stuff, because you will see it. It has a power law slope. It has a terminal power law slope. You will see it. So small angle scattering has a challenge in the fact that it averages over everything, and it averages also over all illuminated area, where you can go in imaging and pick a grain which has lots of your little precipitates of your favorite which you want to see today. You cannot do that typically with small angle scattering unless you're going to make your beam size really small, and then you somehow have to find the grain anyway. So most of the time you'll basically get this volume averaged information in small angle scattering, and you cannot go in and somehow miraculously ignore some areas and study only some. It generally is difficult. And there are ways how people try to do that. So I'm not saying this is globally true, but this is mostly true. And also the contrast mechanism of small angle scattering is kind of an interesting beast. For X-rays, it is an electron density, and in first approximation, it closely follows regular density, standard density in grams per cubic centimeter between the two phases. And it's, again, there are some exemptions, but this is a relatively good first estimate. So if you have a gold inside plastic, it's going to scatter well because the gold has a high density, has a high electron contrast, whereas the plastic has a low density, and so the difference between them is huge. In neutrons, it's even more complicated because they were talking about the neutron contrast, and there is basically no relationship with the density of the material to start with. So figuring out what is visible for X-rays and neutrons and optical microscopy is an interesting question, and oftentimes those are different things. And it gets interesting because oftentimes you can take a complicated microstructure, study with all of these techniques, and then combine the results together to get a much more complex information about your microstructure. In other words, it's complicated. However, it's still relatively easily doable to make a guess in a specific case. So how can we model this? And this is one of the ways which is kind of general purpose way, and it has few steps. Number one is you will not get away from measuring at least one sample, a representative sample. It could be the background sample with no precipitates. It could be a sample with known volume of precipitate. You just have to measure one good representative sample. And obtain the data on absolute intensity scale. So you have to put the data on the absolute intensity scale, for example, using glassy carbon. In this YouTube channel, you can find out how to do that with a glassy carbon sample. And then what you have is you have this d sigma d omega, which now is a measurement, an instrument independent measure of the scatters of your sample. Then you can use Irena modeling tool and put in your best guess of volume fraction of your samples and size and shape and contrast. Simply compare them together, and it is easily done, and then you will see, okay, there's a typo here. And this is easily done also for homogeneously distributed samples. So if the precipitates or scatters are all throughout your sample, this is easily done. If for inhomogeneously distributed system, for example, if you want to put a thin layer of the coating on a substrate, it's possible, but you need to do some creative scaling, which is kind of beyond what I want to talk about today. And then I want to present an example. So the example I have is a user provided an alloy sample with a copper chromium zinc material. It doesn't matter what the material is. I'm not going to go in more details on that, but it's basically a hunk of metal. The user was able to produce a very nice sample for small angle scattering from a test coupon. And basically we did a small angle scattering, and I'm going to show you data in a second. User also used a TEM and provided best guess compositions and densities and volume fractions. So I got some information about precipitate, let's call it precipitate EA. And the user said this is about 3 nanometer diameter spherical particles, and it's a precipitation of this material. And based on that, we figured out that with some hand waving, the contrast approximately 170 appropriate Irena units, which you get from Irena calculator. Then we have the precipitate type B, which where the user said it's about 20 nanometer diameter, different composition, again approximately spherical particles with a contrast of about 30. So that actually has much lower contrast than the other one. Also, based on the chemistry, on how much material there actually is of these different precipitating elements, we calculated that the maximum possible volume fraction of phase A is 1 volume percent, and that means all of it was precipitated out. And then for the B, it is about 1.5 volume percent. So actually relatively low concentrations. So, and we measured the sample on SAXS instrument on absolute scale, and I want to walk you through performing the modeling and analysis and giving you the conclusion why this was impossible experiment, why you can do that. So let's go back to Igor. So now I have Igor here, and what I did is I have these data which I exported from Igor before, and we can import them. Now I actually want to show you that you can get 2 types of data out of Irena, and if you do it, you get different ways of putting data back in. So the first one is, which we all know, is we can go in and import ASCII small angle scattering data. That has been in Irena forever, and it's basically a record of data where you have a Q, intensity, and error. This is the most compatible one which you can get through and put it in more or less anything. And so you can select the data. We're gonna go to, someone stole my desktop, and we're gonna say this one is probably txt, now it's a .dat. So I'm gonna see that. I double click on this, that opens up here. I can check the right checkboxes. There's not much else I need to do here. This just came from Irena. It is actually calibrated in centimeter square per centimeter cube per steradian, which is this one here. And I'm gonna set import. And so now what I have is, I have inside Igor, I have the data in folder SAS, imported data, and it says copper alloy here. The next thing what we can do is there's this other form, which is the Nexus file. That is a more modern binary file, and I can do it. There's a Nexus CAN-SAS data importer. I can, again, I'm looking on the desktop, so I can actually go in here and say this one has an extension H5. That's this way. There's nothing else to do. Basically, this one here contains all the information in there, and I can simply hit import data, and it puts the data in there. Also, in this case, it's inside here. And so I can go in, and now I can remove this one here. I can rename that. Can move it around, for example, here, and then delete this object here. So anyway, so now we have the same data in here. The advantage of using the Nexus file, there's a bit more information inside that. It also came through with a Q resolution, which is the W wave. But anyway, so both of these importing to both of these exchange formats work about as well. The one for Nexus is actually slightly easier. I'm going to delete this because we need only one copy. So now we have data in. We can go in, say we have a QRS data, pick it up, and we are looking on data. There is actually a lot of scattering out of this alloy. If you look on that, first thing is, well, I'm not 100% sure what this is, and I never tried to even figure it out. But there is obviously some precipitation or some formation of large particles here. They are relatively large here. And there is actually low Q power law slope. This is quite common for alloys. Alloys are pain because they have these grains, they have grain boundaries, they have possibly some other features in them. And so they scatter all around the place. And therefore, it is very difficult to study weak scatters, weak components of the microstructure in alloys. So let's now think about or see if the user can see whatever they came up with as an explanation they have. So in that case, you go in and you go in modeling, because in modeling you have lots of controls over your models. Let me just make it larger. And so I'm going to pick the data and select a copper alloy and add the data in here. This is now my data for the alloy there. I'm going to go in a model, and now if I remember correctly, we had, it's somewhere up here, so we had a precipitate A, which had a contrast 170, 10 to the 20 in centimeters, and then it has a 3 millimeter diameter. Okay, so we're going to go here. What is this thing? This is a precipitate A. Now, to make it simpler, I'm just going to go we can leave a Gaussian, it's easier. Then we're going to have 170 here. If you need to calculate the contrast, you will go in and use the scattering contrast calculator, logically. So you would use a scattering contrast calculator to do that. Well, I have the contrast, so this one is 170. And then we have, this is distribution of radii. So if there was a 3 nanometers, that's 15 angstroms diameter. And then let's make this really narrow, like 5. Okay. And the volume fraction is 1. Maximum volume fraction is 1%. Let's check on that. So if we look on this, this is a precipitate A. This is a radius, that's a diameter, and this is in nanometers. That's 30 angstroms. Half of that is 15 angstroms. So we're going to just get some precipitate, and then we have a 1 volume percent. And that fraction here, if the data are in centimeters square per centimeter cube, that's actually volume fraction. So that is my 1%. Okay, so now let's see if we do a calculate model, what we have. And that's it. So you can see that this precipitate A will scatter barely around here above that. And now we can go in and add the precipitate B. So we're going to go in and say this is precipitate B. I cannot type, of course. Now what was it? It had a 20 nanometer diameter spherical particle with contrast of 30. So that would be, again, let's make it Gauss. It's easier to think about that. Let's make it 20 nanometers. So 20 nanometers, 200 angstroms diameter, 100 angstrom radius. Give it 20 angstroms width for now. It doesn't matter too much. And this was 1.5%. too many dots, 1, 5, and this was only 30. Okay, and so if I do calculate model, now we see that. So, and then by the way, there's a background somewhere here. So if I go in and say this instrument, there's some background, so that's 10, 1, it's probably about 0.3 or so. And so that would be about background. So let's go back to it. So if we had in the sample the scatters which the user has seen and made their best guess using their TM or a CM or whatever, this was probably TM measurements, we should see this gray scattering. This would be the precipitate B, so that's this guy here, because that's larger particle, that's the 100 angstroms, 10 nanometer radius, 20 nanometer diameter, and the width is something, it doesn't matter what it is at this moment. And then we should see this scattering coming out of precipitate A. So that's the small stuff. The precipitate A has relatively high contrast, precipitate B has the low contrast. It doesn't matter. Whatever we can say on this thing here is that A, there is not that much of precipitate A, if there is any, and realistically, since this is nearly pretty much perfectly Q2 minus 4, and we can do that by going in and drawing a Q2 minus 4 line and then getting the tools. And so this basically is telling you, if you look on this, that this large feature, whatever this large feature is, whatever it is, it has a sharp interface and it follows the power law slope. The Porot slope is followed quite significantly all the way up to 0.1 or more. So it's telling you that we don't see these. Basically, we don't see these. If anything, this may be buried in here. It would be difficult to prove if it's there or not. So it may be there in some sensible volume fraction. But this, if it's present, has to be in a much smaller volume fraction than what we see. In other words, there's a lot more other scattering in this sample, which makes it impossible to simply see these precipitates or whatever particles the user expected. Now, it would be interesting to find out what the scattering of this is. We never went in there, and it will be clearly there's some other parts of the microstructure, except the user simply gave up the moment when they figured out their favorite particles which they need to see is impossible to see using small angle scattering. They basically disappeared and went after other technique, which is probably the right thing to do anyway. Small angle scattering cannot answer all the questions in the world, so you have to pick the ones which you can get answered from that and find other tools if you need them. So anyway, so I think this hopefully explains how relatively quickly and easily, with a one measurement of representative sample and your best guesses, you can reasonably well predict if you can or cannot see that specific type of scatter in typically more complex materials. You can try to model more about the microstructure if you have more data. You can try to be more precise, but this is typically good enough to tell you if you should even try a bigger, more complicated experiment. And that's also, the fact that you need, the important thing is you need a representative sample and obtain the data on absolute scale. So if you need to obtain data on absolute scale for something like this, don't just ask people who have the techniques, like come to us at the APS or come to other places which run small angle scattering for users. We'll be typically happy to measure one or few samples for you in order to prove if your experiment is doable on this technique, and basically give you a head start on that, so you can somehow then propose a good project and not waste time on making many multiple samples just to find out that it was a wasted time for you. So if you want to come to a SAXS instrument, you can come to us and ask for help with this. That would be USAXS, small angle X-ray scattering, here USAXS X-ray APS-NL.gov. We do have a mail-in program in case you need to prove this. There is a, where did I put that thing? There should be a mail-in program link somewhere here. There's a mail-in program here. So we typically can provide some access to time. There's a whole dedicated page, and in here there's an explanation what type of samples we can do and how you have to provide them and what you need to do. And typically, you send us a sample or two, and we then can provide you with good enough data that you can make a decision, and then we can go from there. Okay. Anyway, good luck, and if you have any questions or problems, feel free to contact me again.